Hello, Nikki.
Hello, Andres. Happy to see you back.
Yeah.
And to see Lubian as well. Must be the morning time.
Yes.
Yeah, quite
Ni-
early. Yeah.
9 a.m.
9
9 a.m.
a.m. Yeah.
It's my breakfast.
Okay.
And it's winter.
Oh, it's
Only.
Yes,
winter.
it's
Yeah.
winter.
Is it okay if we wait for one more minute just to admit all?
Yeah, sure.
Yeah.
I only have to teach in at 11, so for me, I have.
Okay.
May I introduce you? Rodolfo is here. Log. Hello.
Hello.
Rodolfo is a
Hi.
colleague and friend from me, from another city than Buenos Aires, which is called Rosario, close, but another city. And well, he's a close collaborator with us, and well, I invite him to the
Uh,
talk.
nice, nice.
Thank you, Andres.
Nice
Nice to
to
meet
see
you.
you.
And there on the other screen is Daniel and Maria Angelica, also colleagues from Tandar.
Hey, Daniel. Hey, Maria. How are you?
Do you
Hi,
remember from
Hello.
hi,
Nikit?
Nikki.
Yeah.
Hello.
It's long time.
Long time. Yeah, seriously long time.
You are welcome to visit us every time.
Yeah.
Okay. We can start now. So, hello everyone. Uh, welcome to the today's webinar by Professor Jesus Lubian. He is a theoretical nuclear physicist born in Havana, Cuba, who graduated in physics at Moscow State University, MV Lomonosov, and did PhD in physics at Centro de Estudios Aplicados El Desarrollo Nuclear, in English, Center for Applied Studies to Nuclear Development, at Havana, Cuba. Sorry if I'm pronouncing it wrong.
It's
He has
okay.
he has experience in nuclear physics, working in the theory of nuclear reactions between stable and unstable nuclei at low and intermediate energies. He is currently working as an associate professor at the Instituto de Física of Universidade Federal Fluminense in Rio de Janeiro, Brazil. So I welcome him and
Thank
hand
you.
over to him now.
Well, thank you very much for the invitation. Uh, Today I will
Pleasure.
talk about competition between collective and paired correlation in neutron transfer reaction, specifically oxygen 18, oxygen 16. I will show also one example in other to neutron transfer reaction, not only in this. The outline of my talk, I will start talking about nuclear spectroscopy via transfer reaction between heavy ions using oxygen 18, oxygen 16 reaction. I will show results for reactions involving carbon 12 and 13 targets, oxygen 16, nickel 64, silicon 28 at 84 MeV incident energy. This experimental data were taken in the Laboratorio Nazionale del Sul in Catania, Italy. I will show also some results of other groups. I will give a brief description of the theoretical methods used to perform these studies. There are coupled reaction channel calculations. In the case of two neutron transfer, two-step CCBA, or DWA. And I will also introduce a model we developed during these studies. It's a microscopic cluster calculations. And I will apply also this methodology to multi-nucleon transfer reaction in light systems, specifically beryllium 9 plus beryllium 7 to neutron transfer reaction. Then I will give conclusions. And before the conclusion, maybe if I have time, sorry, I didn't ask you how many times do I have.
Yeah, you can finish in 1 hour if possible.
Okay. So I think I will finish later than that, but okay. And then I will talk a little bit about multi-nucleon transfer reactions in the movement project. So a brief introduction, starting from what the methodology used to study the two-neutron transfer reaction, to study the two-neutron correlation in transfer reaction. Everything started with TP reactions in the past. Most of the results obtained at that time were satisfactory in the meaning that they describe the form of the angular distribution for these two-neutron transfer reactions. But in most of the cases, they need a scaling factor, quite huge scaling factor sometimes. For instance, this is one example there for the ground state. This is the number that was needed to multiply the theoretical angular distribution to describe the absolute value of the experimental data for different states. This is on one example, not the only example, but one of the examples. Okay, what could be the main reason for these discrepancies? One of them is the use of simplified wave function for Triton. The model space used it because at that time the people didn't have the power machines we have at present. They usually use the zero range approximation that is not used almost anymore. Almost nobody know how. This is it's difficult to find even how to do that in the present codes. The use of only simultaneous transfer. They didn't consider the sequential transfer of the two neutrons. And in my point of view, the main problem was the numerical simplifications performed during the solution of six-dimensional integrals in the T-matrix calculations to determine these transitions amplitudes. The main reason that we do not use the Triton at present is because this Triton for safety reason has been prohibited. So we need for that another kind of reaction, and one of the very good candidates to do that is the oxygen 18, oxygen 16 reaction. Of course, there is not only that, we can have, for instance, also helium 6, helium 4, but in this case, we have a competition between neutron transfers and breakup, or we can have a beryllium 9, beryllium 7 that I will show it later. In this case, the breakup is not so relevant like in the case, or might be not so relevant like in the case of helium 6. And of course, there could be another reaction with neutron rich nuclei. Well, concerning the theoretical models, the main ingredients we use in our calculations, we perform exact finite range CRC calculations. And 2 to 4, I put here 2 to 4 because I will talk about Newman project concerning to double charge exchange. In this case, the competing transfer channels are up to 4 transfer reactions. So that's why I put here 4, but in the first part of my talk, I will concerning 2 CCBA or DDBA calculations. We always use prior representation, although it is well known that if you use in DWA calculation to neutron transfer, to particle transfer, prior post representation, you have a cancellation between non-orthogonality terms and direct transfer, but this is only in prior representations. We have shown in some of our calculations that the transfer from excited states may have contribution to some specific state of more or about 20%. So it cannot be ignored. Of course, this depends on each case. We always use complex Renan, and we consider non-orthogonality correction due to the no orthogonality between wave functions in different mass partitions. The potential, the real part of the optical potential using our calculations always will be the San Paulo potential, although sometimes we use other potential just to compare that our results are model independent. The potentials used to derive the four factors are always good saxon for the potential that has radius and diffuseness fixes, and the depth of this potential are varied in order to describe the experimental separation energy of one electron or whatever we are transferring. The deformation parameter for collective excitations we always take from systematics, although they are determined for B, E, lambda experimental values. You can have experimental error, but we always take the mean value. We don't vary because if we want to study some effect, if you start varying parameters, then you can miss the main physics you are trying to study. The spectroscopic amplitudes mainly are calculated by shell model, core shell model calculations, but in some examples we have used it also the interacting boson model too, the interaction boson Fermi model, or the quasi-particle random phase approximation. So continue with the theoretical model. What we have to do in this case is to solve a system of coupled equations when we have the diagonal part, the inelastic excitation of different multipolarities, and the overlap between different mass partitions concerning to transfer chance. Sorry. The single wave functions are determined always in the LS coupling to determine the quantum numbers of the states, and having a core with some spin, we have to couple the spin of this particle to the spin of the core. They are a solution of the system of equation. In the case of two particle transfer, we can have two main models, or they are usually using two main models. The first one is the so-called string cluster model. The string cluster model is where you have the two nuclei frozen, and they are considered that have not internal structure, but they are separated to the center of mass of the core with some specific quantum number, main quantum number, and the angular momentum. Is considered that these two particles are in the 1s state with the spectroscopic amplitude equal to 1. A more microscopic calculation is when you consider the coordinate of each particle on its wave function, and then you perform a Moshinsky transformation to determine the spectroscopic amplitudes of these overlaps. And now you describe the internal coordinates of these two nuclei by this coordinate row, and the center of mass of it is concerned relative to the center of mass of the core by small r. In this case, the wave functions are described in these ways, and the thematics of to derive the cross sections are determined in these ways. This is for the direct transition. That this method is called independent coordinates model. That is, in this case, is the picture here for the reaction oxygen 18 plus calcium 40. This is a direct transfer of the two neutrons, and the sequential is when you pass through an intermediate partition. In this case, fluorine 19, potassium 39. First, you transfer one neutron, then in the second step, you transfer the second neutron. Concerning the potential we use is the San Paulo potential, as I said, is a double folding potential in which we fold the matter density of the two nuclei by a nucleon-nucleon interaction, usually taking as N3Y interaction. And the San Paulo potential is the local equivalent representation of the San Paulo potential is this folding potential multiplied by a string coefficients that is determined by the relative velocity between the two fragments, is this V here. What is usually called the San Paulo potential systematic is the use of some systematic for these matter densities based on Dirac-Hartree-Bogoliubov calculation and experimental data of electron excitations. And from the fit of many nuclei, the systematic for this matter density was obtained like this. The radius is this formula, and the diffuseness is taken as 0.56 Fermis. Then the optical potential we use in our calculations for intermediate and final partitions, we always use this the San Paulo potential for both real and imaginary part. The real part with the strength coefficient 1, and the imaginary part with the strength coefficient 78. This has been proven to works very well to describe the elastic scattering of many systems in a wide energy mass region at energies far from Coulomb barrier, when the coupling to other relevant systems could be important. And in the case we are far from the Coulomb barrier again, we always can excite the continuum. In this case, for the instance partition, we use in CSC calculation and CCBA calculation this procedure when we multiply the imaginary part by 0.6 and we include all the relevant couplings in the calculations, I mean in elastic and transfer channels. So this decrement of the imaginary strength coefficients is due to the coupling to dissipative channels like something in the continuum or deep in elastic or something like this. So, but one question we can ask if the San Paulo potential systematic always work. Well, from our experience, in most of the cases, it works perfectly well. But for instance, we are using here all the time oxygen. We will use here in our calculation all the time oxygen 18 and oxygen 17. From then, if you remember in my previous transparency, the diffuseness for the matter density for the systematics is 0.55, 56. But it has been obtained from the analysis of quasi-elastic barrier distribution that for oxygen 18, this value is not valid. So we have the correct value, or the definite value for this nucleus is 0.61 or 0.60, something like this. And in the case of oxygen 16, as it has only one extra neutron above the core oxygen 16, what we have is a little bit larger, because in this case we don't have a pairing correlation that is present between the two neutrons in oxygen 16 ground state wave function. Another example that has been analyzing very recently, this is work when it was analyzed, it was a silicon 28 that is a deformed nucleus. A silicon 28 and aluminum 27 that is about the same, is the same silicon 28 with one hole in the P3 half shell for protons. So the authors, I am one of the authors of this work too, proposed that in this case, in order to describe the elastic scattering at high energy, 24 MeV, it was needed, the way to describe that was to increase the diffuseness in order to take in a mean way this, the formation of this nuclei was to put 0.62. In fact, I was not completely satisfied with this approximation, and then I show here a comparison of matter densities with in the case we use 0.55 of the systematic and 0.65. We see that at the origin they are quite different, and also at the surface. And then a comparison with the Dirac-Hartree Hartree-Bogoliubov calculations with an experiment, and we see that these calculations are quite near to the experimental data. okay, what happens with the cross section is still in progress because I'm doing this with an undergraduate student and it takes more time. But also we have analyzed recently argon isotope neutron rich normal argon isotope and potassium. These again are matter and proton uh, distribution from systematic of the São Paulo potential, and uh, again from Dirac-Hartree-Bogoliubov calculation, we see that there are some difference between the systematics and the more realistic calculation that will provide differences in the elastic scattering are also mainly and more important in fusion. You see here is a coefficient of about 2 difference in fusion cross-section. So what we can say that the São Paulo systematic is a good approximation, is always a starting point, but one have to be very careful if it is possible to have a very precise calculation. I know that Leandro is in the audience here. I know they have been published very recently a new version of the São Paulo potential that have a correction for specific matter density of marriage nuclei. If he wants at the end, he can make some comments on this. So let's start now our analysis of the experimental data for oxygen 18, oxygen 16 reactions. This is a very good candidate to study the pairing interactions because the wave functions of the ground state should show this characteristic as the core is the oxygen 16. We can consider it very well is at inner core. And in order to study this pairing correlation, we can try the reaction with different targets, with different mass, in order to see what is the effect of this pairing correlation in the two neutron transfer reaction. I want to say that I am calling here pairing correlations, but if I would be more exact, I would say only correlation, because usually when the people say pairing correlation, they take into account only the two antiparallel nuclei in the same orbit. And if you looking out in papers, I am not sitting here the spectroscopic amplitude because they are huge tables that are already reporting our papers. You will see that we have correlation not only between two nuclei, two nucleons that are in the same orbit, but nucleons that are in different orbits too. And not always the main components comes from the main component comes from the two nuclei that are in the same orbit. Sometimes they come from the nuclei that are in different orbits. Of course, the pairing correlation can exist only between them, but it is weaker, as everyone perfectly know. So the first calculation we performed were for the carbon for 12 target. And in this case, the experiment was performed two neutron transfer in carbon 12 target and one neutron transfer in carbon 13 target. So from the experimental point of view, you already can realize that the final state are completely different in the one neutron and two neutron transfer coming to the exactly the same nucleus. So this already is a clear evidence of the pairing correlation, as I will show you in the next transparencies. As I already said, the three approximations were done. The first one was the extreme cluster model in CHC calculation. This corresponds to the direct transfer of the cluster of two neutrons to the target. The relative motion of the two neutrons is completely frozen, as I said, and they are separated to the center mass with the quantum numbers that you have to conserve. You have to convert the quantum numbers of each individual particle to the quantum number of the cluster relative to the target, and you have to conserve the total number of quanta. You only consider in the wave functions only the 1s state with the spectroscopic amplitude equal to 1. We also performed independent coordinate CLC calculation for direct transfer and CCBA calculation for sequential to neutron transfer. So remember that CCBA calculation means that in the entrance and in the final partition, in our case only in the entrance, we have couplings to infinite orders, so the collective state are considered, especially the one of the oxygen 18, the 2 plus state, the first 2 plus states, and the transfer between different partitions. In this case, I'm taking the first order. So in DWA calculations, it means in order one direction. So as a perturbation to the main channels. So here are the results for these carbon 12 oxygen 18 reactions. The name of the models correspond to the colors users for the theoretical results shown in this figure. So this is the ground state. In both cases are the same final nucleus, carbon 14. In the left is for the 2 neutron transfer. In the right is for the 1 neutron transfer. One see that the states that are populated for both more intensively populated for both reactions are completely different. This is already a proof for pairing correlations. For the ground state, one see that the independent coordinates, that is direct, dominates over this sequential. For the excited state, this is more visible. And we see that for the ground state, the cluster model works reasonably well. For the excited state, we have over prediction. So this is a model space used in our calculation. It's a limited model space, but nevertheless, it's enough, as I will show you in next transparency. And we see that we also describe quite well the 1 neutron transfer too. So we observe clearly here the presence of 2 neutron correlation in the carbon 14 ground state, because the direct transfer was the dominant channel. Strong selectivity of the populated state. So the one that are transferring 2 neutron transfer are completely different than the one that are transferring observing the 1 neutron transfer. And what is very important is the absolute cross-section were reproduced without any scaling factors, as I told in my introduction. In the past, the people, in order to take the absolute value that are quite well described here, they need to have strength coefficients that sometimes goes of the order of 100. So our next step was to consider the carbon 13 target in order to study if this extra neutron we have now it will somehow destroy or perturb these 2 neutron correlations during this 2 neutron transfer in the midfield of the 2 center, of the 2 core of the in the projectile and the target, and the residual nucleus. Here the experimental spectrum, where we see that between the 1 neutron separation energy and the 2 neutron separation energy, there is many quite narrow resonance corresponding to the 2 neutron transfer population of different state of carbon 15. And also here, above the 2 neutron transfer, we see a bond that we identify as the giant pairing vibration of the 2 neutrons. I will do a small interruption here to talk about a little bit about this giant pairing vibration that was observed not only in carbon 15 but also in carbon 14. These are the experimental spectra sorry, obtaining. The lower states was already known. What it was new was this bump observed here for carbon 14 to carbon 15 that were predicted by Broglia in at the end of the 80s, and the energy observed experimentally coincides quite well with the predictions. These are the angular distribution corresponding to carbon 14, and this is the ground state and the first excited state and the GPV. For carbon 14, the ground state for carbon 13 and the GPV. In this case, we performed 2 kind of calculations. One of them was the CRC calculation. When we were increasing, we put an extra 0 plus state artificially, and we increases the energy until we get to the 2 neutron separation energy, where some instability start to appear. What we observe is that the step of the angular distribution is only reproduced by L equals 0. The other one goes down faster than the experimental data show. And this is also a state-of-the-art transfer to the continuum calculation. because in this case it's not usual calculation found already in the literature. For instance, for four-body CDCC calculation, where you have only the ground state and already the continuum. In this case, you have 12 method of separation energies. You have a lot of excited state that have to be included and almost impossible to be included. So this is just a naive calculation, but you see that the order of magnitude is completely well reproduced. This was very important because the giant dipole and quadrupole resonance were many times observed and described. These correspond to the particle Hall section of the interactions. When you have, as everyone knows very well, this giant dipole or quadrupole resonance are huge bumps that appear in the continuum and are produced to the correlated movement of many nucleus in nuclei. In this case, this corresponds to the particle. In this case, or if you take, if it was not a stripping but a pickup of two neutrons, you can have also the whole sector of the interaction. This was predicted that should appear not as a huge bump, but small as is observed, because in this case participate only two nucleus. Sorry, let me take a little bit water. So come back to our carbon 13, carbon 15 reaction. We have here, here are the scheme of the coupling scheme used in the direct transfer and in the sequential transfer when we have intermediate partitions just for projectile and target. And what we see is that the cluster models in this case overestimate generally. This is the ground state versus excited state, the second excited state. But again, we see that the independent coordinates describes quite well the experimental data, and the independent coordinates, the sequential transfer is the mean value is lower always than this direct, so the pairing correlation was not perturbed by these extra neutrons that appear in carbon 13. For higher excited state, we obtain again a very good description using these independent coordinate models. And for other more higher states, we have a more over prediction, but nevertheless, always the direct to neutron transfer is higher than the sequential one. Here we come to the model we call microscopic cluster model. That is nothing else that we have the spectroscopic amplitudes for each nucleon. Instead of ignore completely the spectroscopic information we can have of these two nucleons, we will still consider that they are transferred as a cluster without internal coordinates, but we will not consider only the possibility that these two neutrons are in the 1s state. So we perform Moshinsky transformations in this case, and we perform a transformation from JJ coupling to LS coupling. We obtain the spectroscopic amplitude for different combinations of these single particle wave functions, that wave number of the wave function we have in for each nucleon, and we obtain the spectroscopic amplitude for each combination. So this is quite similar to the independent coordinates calculation are already performed inside the Fresco code. But the difference is that here, when you put the information in the Fresco code, you put all these individual spectroscopic information, and the Fresco code does everything but, internally. In this case, you externally can identify and separate each component if you want to study data, as we did in this case. So here are in black is the microscopic cluster model calculations, which you include only the 1s, but not with the spectroscopic amplitude equal to 1, because if you do that, you will obtain what is the string cluster model, that is what we have in the previous transparency. So now if we increase besides the L equals 0, we also include the L equal 1 component of the wave function of the internal move of the internal wave function of these two neutrons. We see that we obtain quite good description, except for the first excited state that this is because the model space we use is not large enough. But if we look for the high excited state, Again, we have quite good description of this high excited state. For the much higher state, we have a small on the prediction that might be caused by this the absence of this D3 half component, but may be relevant. Then, in order to see if the ZBM model used for this calculation was enough, we performed for the projectile. We studied the reaction oxygen 18 plus oxygen 16. In this case, the initial and final partitions are exactly the same, so we have to be careful on that because you have to distinguish between elastic and elastic breakup because they are completely the same channels. So we use two interactions in this case. The one that we were using until now, that is called the ZBN interaction, that in which the valence orbitals, sorry, are these ones, and a much larger model when we have that the helium-4 is our core, inner core, and then we add a subshell below this P1 half, this is the P3 half, and we add this D3 half. So this is the experimental spectrum of this reaction. These are the experimental states that were resolved or the ones that were not resolved. That called as these 1 to 5 here in the spectrum. These are similar to the spectrum observed in the TP reaction. Sometimes some state could be resolved in TP reaction because they are usually the resolution is much better because the mass of the triton is smaller than the oxygen. But what is also important here that we calculated the elastic scattering and the transfer, and we compared and we performed the coherent sum of them, and we see that in the angular region where the experimental data were taken, the data correspond exactly to the elastic transfer, and the only contribution at backward angles are important from the elastic channel. So here are the comparisons of the calculation with experimental data. One see that the PSD mode, this is for instance for the ground state, lies below the experimental data, and the ZBN describe better the experimental data. You will see here that there is some shifting angle to the right compared to the experiment. We realized it sometime later because at the beginning when we started it, we found in the Sattler book that you can use half of the of the separation energy for each neutron when you are doing this kind of independent coordinate model calculation. But then we realized in the future that we can put the specific separation energy of each neutron. If you do that, you will see immediately that you have a shift to the experimental data, improve the agreement with the data. But at that time, we used this approximation because maybe in the past, the people, as I said, the machines were not so powerful as we have now, and they try to simplify as much as possible all the calculation. So what we see here is that, again, the correlation is important as expected because if it is the projectile in the case of oxygen 18 and carbon 12 and 13, you cannot find out that in this case the correlation should not be important because this was our projectile and the overlaps were present there. So now what we see that the ZBM interaction is enough to describe this light nuclide. Also, we studied the high excited state, I'm not showing here, but in this case, the PSD mode, because we need larger model space in order to describe the high excited state, becomes more relevant. Then we come to medium mass nucleus, that is nickel 64. In this case, this is the model space we use. This is the nucleus that it is not near the double magic shell, that is in the top of the complete availability of the shell model calculation. So this means that you have not to put constraints in order to populate one or other shell. You can put all the possibilities and you can still run this to analyze this matrix without many problems, numerical problems. So This is the the overlap for the projectile and target in the case of direct to neutron transfer and sequential through the intermediate partition. These are the results of the angular distribution for the ground state and for the first excited state of nickel 66. This is the result for the cluster model. We see that, as expected, in this case, the cluster model doesn't work well because it's not easy to imagine that nickel 66 could be a core of nickel 64 plus two neutrons. So the interaction between so many particles here will not allow us to say that this is a cluster in any case. So the shell model gives a reasonable description. What is important at this point is that we reproduce the bell shape characteristic of two neutron transfers in the intermediate mass region. And for the ground state, we have still strong contribution for the pairing correlation, while for the first excited state, we have the predominance of the sequential one. We have to remember that nickel 66 is already a nucleus that have a collectivity in the first excited state. So this is an evidence that the multi-nucleon correlation predominates above the pairing correlation or two-nucleon correlation in this case. This has a result for the interacting boson model 2 and interacting Fermi model because in this case we have an odd nucleus here. So these are the description of the spectrum, very nice description that usually is obtained in the IBA interaction. And here the description of the experimental data was strongly improved. You see that in the ground state, the correlations, the two neutron correlation prevail as was predicted by shell model, but with a better description of the experimental data, and the 2+ state was very nicely described also. In this case, that the predomination of the two-step process was in here due to the collectivity of this state. To support this conclusion, we compare here the B2 transitions for these were the two of the states studied when the pairing correlation was found relevant. You see that these values are small, but in the case of all the nuclei where the sequential transfer was found more relevant, the B2 values are bigger. This case I will show in the next transparencies. That is the other system we studied, the transfer to silicon 28, giving silicon 30. So here are the results for this silicon 28 target. This has the sketch of the overlaps of the projectile in the case of the direct transition. This is projectile target. And this is for the sequential when we have the intermediate partition. This is the model space. In this case, is PSD mode because this is not, this is the form nucleus, so you need a large model space for both protons and neutrons in order to describe the collectivity of these nuclei. I'm not showing here, but we always check the states. When we perform this shell model calculation, we compare with the spectrum of all the nuclei involved, also the reduced transition probabilities between these states. We compare with the experimental data in order to have agreement with them. Here are the results for the angular distribution of two neutron transfer state for the ground state, first excited state, and a mix of some excited state. We see again that the cluster model overestimates, not a good model. But in this case, the ground state is, okay, the quality of the experimental data are not so good in this case because of statistics. And we see that for the ground state and for the first excited state, and in general for all the states, the two-step process here is predominant due to the collectivity of all the states that was already mentioned in my previous transparency. The B2 is big for this system. So one question we asked to ourselves is our theoretical calculations, our theoretical model, described only this transfer reaction, but also we can describe elastic scattering, all the channels that could be measured that were not measured in that experiment because the facility was not prepared for that. So we find elastic scattering for this oxygen 18 plus silicon 28 at another energy. So what we did is just change the potential correct the potential for the energy, for this energy, and without changing anything in our input file, and compare with experimental data. You see here that the description is quite well. Some training changes in these uh, betas or this strength coefficient might be necessary in order to get a perfect description, but this was not the scope of our work. You know, if we obtain already the order of the magnitude in quite reasonable way, it is enough for us. These are the results for an Indian group where they observed that in the case of oxygen plus lead 206, they obtained that the sequential is dominant to the direct one. So this means that that the sequential and coherent correlation depend on mass and might depend also on energy. So it's something that you cannot say that it's always like it is in that case. So the conclusion to this part is that we have studied all these two-neutron transfer reactions using these four models: a string cluster model, independent coordinates, and the microscopic cluster model. There was no need or no happiness factor to reproduce the absolute cross-section. For the carbon-13s, the two-neutron correlation was present even, so the presence of this extra neutron does not destroy the two-neutron correlation during the transfer. The two-particle correlation dominates the carbon 15, 14 and oxygen 16 reaction for the low-lying states. Not only for the low-lying states, because for excited states also it happens. In the case of nickel 66, the 2 prostate was dominated by collective excitation, so the pairing correlation or the correlation between two particles was not the most relevant one. And in the case of silicon 30, it happens also in the ground state that is also collective. So one important thing is what happened in the two proton on deuterium transfer, because this correlation might be happening also in this case. So I will show you here later some results for proton-proton correlations. For deuterium, we are also performing some calculation. In fact, we have already some results, but they are still not published. That's why I'm not showing here, because I didn't have time to ask to my collaborator if I can show the experimental data that are not published and so on. So these are a result of experiment performed in Peloton in Sao Paulo for the beryllium 7 beryllium 9 reaction. In this case, the initial partition and the final partition are the same, but in this case, the beryllium 7 is not an inert core, as is the case of oxygen 16. Nevertheless, in our calculation, we didn't consider the core excitations correlated to the two neutron wave functions. So we consider it as inert, but of course we consider the spin of beryllium 7. We didn't ignore in our calculation. In this case, we also have to be careful to the coherent zoom that could appear between elastic breakup and elastic channels. Again, the elastic, what is called elastic was measured for very forward angles, and what is called transfer was measured at backward angles. So they cannot, in the region of the interference is this region where the interference is relevant. I'm not shown here, in the paper is shown, but it's not the place when we have experimental data. So again, what we see is that sequential transfer has a much lower cross-section than when we transfer the two neutrons coherently to the final state. So even if the core is not inert, the correlation between the two transfer particles was found very relevant. In this case, as it is not quite spherical nucleus, we again use a large model space. We use a PSD mode interaction. These are again the overlaps of the projectile target that is the same in the direct and the sequential transfers. So the conclusion for the two neutron transfer reaction, we see that the neutron-neutron correlation is not only important for oxygen 18, oxygen 16 reaction or TP reaction, but also in reaction where we have not an inner corpus to neutron configurations. The relevance of the neutron-neutron correlations depend on the degree of the collectivity of the final states and also of the mass of the final states. As I already said, the look is to study the two proton and neutron proton transfer, to study proton proton and neutron proton correlations. So here I come to more steps or multi-nucleon transfer reactions. This is concerned to the Newman project. The Newman project is a project devoted to the study of double charge exchange with the objective of determining if this is the opposite reaction of double beta decay that the people are trying to find if could exist a neutrino-less double beta decay in order to determine if neutrino are Majorana particle or not. So to try to develop a fundamental theory below the standard theory where the lepton number will be not conserved. In our expertise in expertise in multinuclear transfer reaction is very important in this case, because even if you want to study this kind of reaction and you say that this is double charge exchange, you have no reason to ignore the multinuclear transfer reaction that could compete, or even the sequential direct single charge exchange reaction that could compete with the reaction you are supposing you are measuring. So in order to say that the cross section you are measuring is a double charge exchange, you have to calculate all the competing channels that appear in this diagram. So you have to have, for instance, two protons, two neutrons, or one proton, two neutrons, one proton, one neutron, or neutron, proton. So all the possible channels are shown here. In fact, we have calculated all these competing channels. As this is not published, just showing here the preliminary results. I just can tell you that we are about to publish these results, but the preliminary results shows that might be that these transfer reactions are not relevant or are order of magnitude lower than what is measured as the double charge exchange or sequential single charge exchange reaction. But one important thing in order to be confident on these four multinucleon transfer reactions is to show that we are able to describe all these steps here. So this is something that the Newman projects have been considered also too. One example of this is already published, that's why I'm showing here, is the same reaction I showed in my previous transparency. This is not the only reaction in the Newman projects. There is about 6 reactions of double charge exchange that are proposed to be measured. And in all of them, also will be measured elastic scattering, multinuclear transfer also, in order to prove that we are able to calculate and compare with experimental data all these reactions. In this case, it's the neon 20 cadmium 160 reaction. I will show here the two neutron and two proton reactions. This is the model scheme in the case of direct and sequential. As I show in the case of nickel, you see that this is already not light nucleus, so you see the bell shape here, typical for medium mass or medium mass heavy nuclide. Sorry. So these are the experimental data. In this case, there is no experimental angular distribution because the cross sections are nanobars, are very small cross sections. These are the experimental data. The error bars are large because of the low statistics. And these are the results of our calculation. We see here that the collectivity of cadmium is well known that is not high, but the collectivity of neon is high. So we see here that the sequential is higher than the independent coordinates, as we obtained for the deformed nuclei already mentioned in my presentation. but we see a good accordance with the experimental data, a good agreement with the experimental data. In the case of the two proton, in the case of the two neutron, in the case of the two proton reaction, the bell shape is smoothing. This have been observed in all the two proton transfer reactions in the literature too. Again, here are the couplings, the overlaps for the direct, projectile, and target, and in the sequential you have, as these are more heavy nuclei, you have a lot of states to be considered, so a calculation very time consuming with quite complicated calculation. But again, we have good agreement with the experimental data. You see we have here tested several shape model interactions. In this case, we compare also interacting boson model results. In the case of the two proton, we also performed, for the first time, we was performing quasi-particle random phase approximation to derive the spectroscopic amplitudes to compare with this calculation. And again, we have quite good results. Also, in this reaction, was the pilot system studied in the Newman project, was oxygen 16 plus carbon 40, with the same procedure, with the same exactly the same potential, everything the same. We see here that we have a very good description of the angular distribution, and you see that they are measured to the very low cross sections. I would say backward, not backward because it's 25 degrees, but concerning to this energy is, let's say, backward angles. The inelastic excitation are quite well described, and the single charge exchange is reasonably well described. So this means that the wave functions we have in our initial partitions and final partitions are well described. Another work is, this is another system that will be studied in the Newman project. So this already we started the two neutron, two protons, whatever, multi-nucleon transfer calculations. By now, the elastic scattering was already measured and elastic cross section. Using the same procedure, you see that we describe very well the angular distribution to the very low cross sections and inelastic cross sections too. So what I have shown to you is that we have performed many multi-nucleon transfer reaction calculations. All this part of the project, this part is in project. This is the working group concerning to all these calculations. We also have resolved for PT reactions in lithium 11, but as has been not published, I didn't show it. So thank you very much for the attention. If you have any question, it would be my pleasure to answer, if I can.
Yeah, thank you so much for a very nice presentation. The session is now open for discussion. You can unmute yourself and can ask.
Hello, myself, nice to see you, Professor Lubian again. Myself, BK
No,
Nayak
thank you.
from Mumbai.
Thank you for being here, Nayak.
Yeah, I just want to ask you, all these two neutron transfer you studied, they are all having positive Q value?
For lithium, what?
Positive Q value. What is the Q value is positive or negative? Q value, transfer Q value.
The Q values are positive Q value. Mostly positive, yes, or near zero sometimes, but mostly in this case, all of them are the ones I shown here. They were selected to have a positive Q value in order to guarantee larger cross section in order to measure. So the system and the energy were determined by matching conditions using the I forgot the name of our guy that recently died, passed away, sorry. Well, the matching condition is a semi-classical matching condition in order to determine the optimal energy, the optimal energy excitation. So the one that we could measure, of course, calculate.
So whether this is sequential or simultaneous transfer, that will depend on Q value of the transfer Q value?
Wherever they are sequential, in all the steps, they are positive Q values. They have positive Q values.
Okay, thank you.
Welcome. The only one that is zero Q value is the the beryllium 7, beryllium 9, because in one you have positive, in the other you have negative, because you have the same defined. Also in the oxygen 18, oxygen 16. So in one step you have positive, and in the second you have negative, or vice versa.
It's a long time back we had done this oxygen 16 and oxygen 18 on yttrium, 170 for yttrium. Because all your results are from structure measurement, but we did just projectile-like fragment measurement. We also observed this same simultaneous, transfer of the 2 neutrons.
Okay, if you want to have calculation for this data.
Yeah, that's what I'm asking. That our paper was sometimes in 2001.
Okay, just let me know. We can.
I can give you the reference. It was PRC volume 64. 014609.
And what was the target? Tell me.
Yttrium 170 for YB.
Yttrium. Okay.
Oxygen 18 on yttrium. We have compared result oxygen 16 and 18.
Perfect.
Thank you.
Okay. So, good morning, Professor Lubian.
Good morning.
After 3 years,
good evening.
Because formally I was working with breath in a South campus. So, okay, so nice to see you. But here I have a simple questions regarding your density. So, how you obtain the density for the interacting nuclei here?
Well, in the San Paulo potential systematics, they are obtained by a simple formula.
Yeah, I saw that formula. So here my question is that that simple formula is how appropriate to consider the structural information of the exotic nuclei that we take in our interaction.
Okay, I think the best person to answer this is Leandro Gasquez, that is in the audience. They have a new version of the San Paulo potential. I think that many of these, for instance, this is a neutron-rich potassium 49 is a neutron-rich nucleus.
Yes.
In this case, Brett Carlson performed a Dirac-Hartree-Bogoliubov calculations in order to determine proton and neutron densities.
Yeah, also recently he is working with the RSP, relativistic Hartree-Bogoliubov.
Yes, they are relativistic calculations, relativistic matter density.
Also working for the exact pairing and also deuteron pairing little bit. So, okay, by the way. So, and about the deformation, for example, few of the reaction you saw that there is also the nuclei in the ground state also even have deformation. I think you have no inclusion of deformation in the calculation, right?
No. In all these, so they are able to calculate the formed matter density too. Okay, but in our calculation, when they give to us, usually they do a mean from all this deformation and give off the spherical equivalent. But this, in the future, we are planning to use these deformed matter densities in our calculation. But this, I have to check with Brett how to do that, because I have to have exact information in order to put in Fresco.
Okay. So when, for example, take the spherical equivalent, it is the multiple expansion or some other method?
Yes. Usually, when you calculate any deformation, what you do is a multiple expansion of the spherical matter
density. Thank you very much. Muito obrigado.
De nada.
Any other questions, comments, remarks?
Leandro, would you like to do some comments about the new version of the San Paulo potential?
Well, yes, I can say something about it. In the version that you showed, what we have is an average of density. So Brett has performed Dirac-Hartree-Bogoliubov calculations for many nuclei, but for sure, nuclei far from the stabilities, they were not included in this systematics. So now in this new version that was published 2 days ago, you can choose the density calculations properly for each nuclei. So you have a huge table with where the code gets the proper calculation for each nuclei, and also for nuclei which has would have n equals to z. We can also the code can also take the experimental densities obtained from electron scattering. So we have to check this new potential. It's
Yes.
just very fresh.
Well, in fact, I am checking it because the result I shown here for potassium are already with these new matter densities. And you see that the fusion cross sections are quite different. The elastic depend
Yeah, yeah.
on the resolution you have. If you have very good statistics, you will see also differences. But the fusion is critical. For
Yeah.
instance, you see here for potassium 47 and argon 44 that are both are neutron rich. You see that the difference between the systematic matter density obtaining from the potential using the systematic density and the potential using the realistic Dirac-Hartree-Bogoliubov calculation are quite different.
Yes,
Here
yes,
is
yes,
a
yes.
factor of 2 at the barrier.
Yes, yes, yes,
Yeah,
that's true.
you have a
Because
huge
when we have also considering like for example the safe degrees of freedom, and if we see the nucleus, we can also take the spherical one in a different angle. Also, we can find the nuclear potential. That is the nucleus potential also quite different from different angles. So
Yeah.
that is actually I want to know that actually it's the any easier way that we can implement or not. Okay, thank you very much, Leandro, and also Lubian, Dr. Lubian.
Okay.
Okay. Is there any other question or comment? If not, let us thank Professor Lubian. Thank you very much for accepting this invitation and presenting your work with us.
I thank you for the invitation. It's
Yeah.
very nice to
Yeah.
have a contact with other people. Some of them I already know here from the audience, but there is other new people. Thank
Yeah.
you very much for the invitation.
Yeah, and I can actually take this time to introduce with our other committee members in the group. I can see some of them are here, and they all can say hi. Dr. Bhuya and
Yes, yes, I know Dr. Lubian personally because I was there for 3 years. So in the Southwest Coast campus, so I know him
Jagandeep
personally.
is also there.
Okay, thank you.
Yeah.
Thanks.
Hi.
Hi. Some people have common surnames for us that I see very often. And I don't know which one is the person I'm talking, because sometimes I see in the papers the surname, but it's not the same person.
Yeah, Singh is a very common surname.
Yeah, it happens. Yeah.
That's what I say. Yours is one example of that.
Yes, I agree. Yes, I probably also had a question. So I see that you, if the chair allows me.
Yeah, sure. Go ahead.
Yeah. So I see that your entire formalism is based on prior form G matrix. So how about trying something with the post form?
Well, the only difference, the main difference in this case, in the prior or post form, is that you use different potentials in interactions. In principle, they should be equivalents. You can even do that. You can use different combinations when you have multiple transfers. You can use, in principle, I usually use the one that I have more confidence. For instance, is the final interaction correspond to the nucleus near the stability, and I use this for this interaction as the more important interaction for me. If the initial interaction is the one that I have more confidence of my potential, I use this prior or post. But in principle, if you are using the correct potential in the initial and in the final partitions, the two calculations should be completely the same.
Yeah, final result is equivalent, but the question of the potentials that you raised. So the different interactions, they would be included in this Hall-Hollow potential scheme equivalently, you said?
Yes, yes. But as already also Leandro said, the potential, the initial version of the San Paulo potential was derived using mainly nuclei near
Near
the
the
stability
stability,
value.
yes.
When you are using here other reactions with systems that are far from the stability region, you have no confidence on the validity of the San Paulo potential for these nuclei. So in this case, I use prior representation when I have more confidence on the initial partition. If I have some mistake in the final partition, I expect that not be very catastrophic to derive the magnitude of the cross sections I'm interested to.
I see, I see. Thank you.
Okay.
Okay. Then maybe we
Okay,
can.
Bhumika, thank you very much for organizing such a talk. And after a long time, I saw Professor Lubian. Very nice and informative talk about the elastic and inelastic cross section, and also little bit discuss about the fusion. So that's very nice.
Thank you.
Thank you. Okay then, if there are no other questions, comments, we can.
And also, I would like to say that we are open for collaboration. So if any one of you want to have some theoretical interpretation or discussion, my email was in the first transparency. You can contact me anytime.
Thank you
Okay.
so much. Okay, then we can close the session for today. Bye bye everyone. Thank you, Professor Lubian, again.
Okay. Bye bye.